I'm Chris Woodgate. I'm the Secretary for the PWI Queensland Division. Robin Stevens passes on his apologies, he couldn't make it tonight. So like normal, I'd like to kick off by acknowledging our sponsors, our gold, silver and bronze sponsors. Without them, these nights can't be possible. They help supply the beer and pizza afterwards. So it's really very appreciative to the gold, silver and bronze sponsors. The past events we've had over this year has been a technical presentation on the February and the March the AGM. I think they both were very successful if you attended them. The upcoming events are the June, we've got another technical presentation, Partners Night in July, technical presentation in August and September, and Brisbane Golf Days in October. The Rocky Golf Day and Regional Rail Tour are scheduled for August, dates to be confirmed still. So that's the events coming up. Tonight we have Daniel Buntine. He's a senior civil engineer at Aurizon. He's currently working within the Network Asset Management team, working on various track engineering projects. He's a chartered engineer with Engineers Australia and registered professional engineering with 10 years experience. Daniel started with Queensland Rail prior to the separation and has since worked on a variety of engineering roles across design, construction and asset management within central Queensland and Western Australia. Tonight I'll be presenting on managing...
Come on, you can do this. Managing and modelling track stability at Black Mountain.
That's the one.
Don't forget your drink.
Thank you.
Thank you very much, Chris. It's an interesting story we've got for you tonight. It's an investigation that we started a couple of years back. When we ran into some troubles, we started looking into it, and the path that we took through the investigation, we ended up somewhere we really didn't expect to end up. So I hope you enjoy the journey. Let me start with a little bit of an introduction to Black Mountain. I assume you're all familiar with Aurizon as the leading rail infrastructure operator in central Queensland. One of our busiest places is Connors Range, which is also known locally as Black Mountain. It's just south of Mackay and just southwest of the sugar farming town of Serena. What makes this particular place special is that it is a pretty challenging section of track to manage. There's a 9-kilometre long downhill grade of about 2% pretty consistently, and you've got 24 back-to-back 300-metre radius curves. And if any of you have ever spent any time in the world of designing heavy haul rail alignments, you'll know that that's not a desirable combination to have. But sadly, we're stuck with it. And what we run on those tracks, it's a duplicated set of tracks, bi-directionally signalled. We run 12,000-tonne coal trains, 124 wagons, and they go down the hill at about 40 kilometres an hour. It's part of our Goonyella system, which is our biggest coal system. It's electrified. It carries something in the order of 100, or this particular track, the up track, carries about 130 million gross tonnes of traffic each year. And for us, it represents the key rail system constraint. So if the operators bought more trains and the port sorted out their capacity and the mines uplifted their production, then this would eventually become our biggest bottleneck on our part of the network. Certainly to cater to the uplift in mining, we've been undertaking some mainly signalling projects to support the growth in traffic in this section. And in 2009 or shortly thereafter, we reduced the minimum headway on that track from 30 minutes to 20 minutes to facilitate further traffic growth. Now, while tonnages since that time as a system have only increased by 20 or 30% from memory, what is interesting is that the loaded track, or what is predominantly the loaded track, has had a disproportionate lift in the amount of tonnes that that particular track has carried. And as you can see, it's up 45% over a 4-year period. And that's because as the network becomes more saturated, that there's a need to run it more and more like a conveyor belt so that trains don't cross paths, removing all the flat junction conflicts that would result, so that you get the best operational efficiencies, But the net effect to us track people is that you get one track that cops all the loaded trains and one track that cops all the empty trains. And that presents a maintenance problem because loaded trains are 5 times heavier than the empty trains. Where we are currently is that during our busy times when the coal price is high and the railings are in demand, we're getting about 40 trains a day on each track at peak times. So if you divide 20-minute headways into 24 hours in a day, that's 72 possible paths. Take out a bit for maintenance and recovery time, and you can understand there's still a bit of room to grow there from that 40 trains per day as a system. Where did we start this investigation? It all began in 2016 when we started to have some track buckles occurring towards the bottom of Connors Range, towards the bottom of Black Mountain. What was interesting about them is that a lot of the time they were occurring not in the middle of summer. So March and April we're seeing track buckles occurring as well. And one in particular that caught my eye in particular was one that happened at the 37.9 kilometre mark on the up track. And it happens 36 hours after a rail replacement. So 36 hours after, we went there, put brand new steel in, and we stressed it to exactly what the design stress-free temperature should have been, or so we thought. So what makes this even closer to home is I was the engineer out there doing the stressing on that night. And when the email came through, 36 hours later, that the track had buckled at this location, my heart sank. I thought, what did I do wrong? What went wrong here? And I became very invested in the process of working out why. We opened it, we found out it was exactly as it was meant to be. One rail was 38, one rail was 36 degrees. So the track was pretty much exactly where it should have been rail stress-wise. So I was happy, nothing wrong went there. So what did cause it? Why were buckles occurring in late March at this location by the coast? And we had a look around and we found a mud hole. There was a mud hole, there was a little bit of insufficient ballast shoulder. So we wrote it off as that at that time. We thought, okay, mud hole, let's fix the mud hole, put the track back in, and everything will be hunky-dory. But that wasn't the case because we just continued to have problems at that location. And certainly a single mild mud hole that was nowhere near as bad as what we see in other parts of the network, that shouldn't have been the sole contributor to this amount of buckling that we're seeing at Connors Range. Then we enter stage left Will Shu, who's a track engineer up in our Mackay office. And he made an accidental discovery, like so many of them, by putting his hand on the rail and burnt himself. That's concerning. That's concerning. So he got the temperature gun out and he shot it at the head of the rail, and that's what he saw there. 95 degrees. That's the temperature he was recording at the head of the rail. So then he started shooting it at the web, what he thought was the web of the rail, and he was picking up 78 degrees after the train, and that slowly rose to 84 degrees. That's well above what you would think a rail temperature would be, even in the middle of summer, even at noon. We generally go off the idea of about 65 degrees is what we'd expect in those sorts of conditions. And certainly, just to check, just in case he wasn't sure that this 95 degrees was an accurate number, he dropped some water on the head, and sure enough, it did start to boil. So that's when we started to consider that trains were causing rail temperature spikes far greater than we previously thought. So we know from all the literature that trains, heavy haul trains in particular, can cause rail temperature spikes of about 5 degrees. There's a lot of literature out there that says that. And it also says that a lot of the cause of that might be due to friction in the wheel rail contact surface. So we thought, okay, let's see where this goes. Let's see what we can measure and see if we can get some greater insights in that. I just thought I'd share with you this video. This is Will throwing some water onto the wheel, a wheel he found stopped on a parked train at the bottom of the hill. And you can see that the water on the wheel is immediately evaporating. That wheel is hot. So the next phase of it was let's collate the facts and let's do a little bit of preliminary testing and see what we find. So we know that loaded trains coming down Black Mountain have their air brakes applied constantly and the dynamic brakes applied constantly as they go down the hill. And what that means that over 9 kilometres, the wheels have their brakes applied and the brake pads are running against the rim for 3,000 revolutions. That's a lot of friction being generated. And at the bottom of the hill at our UCAN hot wheel detector, in the middle of summer, we're seeing temperatures of up to 160 degrees at the wheel. So one morning I was up there on Black Mountain and I just had a temp gun and I was just shooting it at the rail intermittently as we were watching trains go by. And you can see at the bottom here, in one particular case, it was 32 degrees pretty uniformly through the rail immediately before a train. This particular train went by, it had a wheel rim that was recorded at 132 degrees. That caused a 15-degree spike in rail temperature at the head. No change at the bottom, but over the next several minutes, that heat propagated through the rail and started to equalise. But what was interesting is that 18 minutes after that train went by, the average rail temperature through the head we estimated to be 37 degrees, which was 5 degrees above where it was before. So, okay, that seems to be in line with that sort of literature that we'd heard of before. So then we came to our hypothesis that the effect of multiple trains at near minimum headways causes a compounding effect on the rail temperature, because 18 minutes after the train's gone by, it hasn't returned to its previous temperature state. So we talked to our friends in the signaling department, and there are some there who are a bit of fanatics of Arduino equipment, and they knocked together a little bit of a test kit that coupled a Arduino device, a solar panel for power collection, and multiple temperature sensors, and we put a couple of these up and down the range. And what we wanted to do was get a rolling survey every couple of minutes of what the temperature did and how it changed, correlate that against trains and the trains that went through, and try and control for variables like what is the difference between the high rail, the low rail, curve and tangent track, and also loaded and unloaded track. And we also had a temperature sensor on another piece of rail that wasn't in track as a control to see what a rail just sunbaking, how that would go. And we recorded obviously the rail temperatures at the head web and the foot, and also the ambient temperature as well to match that up against. And now I get to tell you about a day in the life of the rail. It's actually 2 days. So you can see up here we've got our 3 sensors. We've got the head in green, the web in red, and the foot in brown. And that's what this graph shows over a roughly 2-day period, where each of these spikes you can see represents a loaded train that passes on the network. A lot of information, but I first want to draw your attention to this first bit here. This is a train-free day. The 8th of August last year was a Goonyella network closure. We had no trains on the network, so this is just rail sitting in the sun, doing what it wants to do. The weather was fine, no cloud or minimal clouds, and that's what it did. So from its nighttime minimum of roughly 15 degrees, the rail rose up to about 40 degrees at noon, held that temperature through most of the afternoon until about 3:30, when the sun went behind the hills and it started to drop again for the evening. The bit that caught my eye and started to think, wow, I think we're really onto something here, was this, the previous night. So for whatever reason, from 6 p.m. through the early evening, there were either no trains due to a disruption, or the empty trains were had been swapped onto that particular track. So we got the same sort of drop in temperature that we saw the next day. But at about 9 o'clock, when the loaded trains started coming down the up track once again, we started to see the temperatures rise. So if we take the red, the web measurement, to be indicative of the whole rail section, you see that temperature spike there of about 5 or 7 degrees, and then it goes down. But it doesn't go down fully before the next rail. So it compounds, and then compounds again. And you can see that at midnight, in the middle of winter, we were getting rail temperatures of about 35 degrees. Given normally we'd expect nighttime rail temperatures to be similar, very close to ambient, that's about a 20-degree discrepancy from what we'd be expecting in that circumstance. So then we take that quiet, no trains day, and we overlay it on top the previous day. And you can see just quite plainly the clear difference that is being made by train operations and loaded train operations very closely together. And as a lot of people know, they try and pump through as many trains as they can just before a closure so that they have something to do at the port. But what you see there is that afternoon, after the solar peak has passed, rail temperatures do continue to climb through the afternoon. And the rail temperature peaked at just under 60 degrees at about 3:30 p.m. And compared to what the rail would have been, that's about a 16-degree premium. And what's made this worse is that that's not even as high as that number could have been, because in the morning that day, it rained, which reduced the temperature of the rail. That's when we knew we were really onto something here. So we took that data, we took the data from 924 trains as they went by and broke them down into, we normalized everything at 0. So then we started from the time that temperature was started to be detected to rise. We went through and saw what is the elapsed time and what is the change in temperature at that time. So each of these faint lines represents a single train. The red lines indicate the head, the green lines indicate the web, and the blue lines indicate the foot, and the black line is a bit of a weighted average of all three. And what can you see here is that in the grey box here, that's 4 minutes. It takes about 4 minutes for a train to pass that section of a 2-kilometre train at 40 k's an hour. So what you see here is that the head, which is measured just under the actual head, what we call the head, it was receiving a median spike, which is this thick red line here. The median spike in head temperature after each train was about 10 degrees, and it occurred a couple of degrees after the train had finished passing. Likewise, the web was about a 5-degree uplift, which occurred a few minutes later. Same with the foot, it had a modest rise of 1 or 2 degrees, and that occurred about 20 minutes after the train had passed the site. And more interestingly is that when these lines reconverge, so over here at about the half-hour mark is when the lines reconverge, and that indicates that the rail has generally equalised again and has a temperature that's fairly homogeneous through its section. That occurs about half an hour later, but it happens about 1 or 2 degrees above where it previously was. So that's basically proved our hypothesis there. What were our key findings? We worked out that curves and tangent tracks had a very small difference between them. But what that did was that it implied that it was less about friction and more about the train braking we were looking at. So the brakes were rubbing against the wheels, really heating those wheels up, and then there was a conductive heat transfer from the wheel into the rail. That's our thoughts on this. Because otherwise, if it was purely about friction, we shouldn't be seeing any appreciable uplift in temperature on the tangent track. It should all be on the curves and very little on the tangent. What was also interesting is we saw a fairly significant difference between the high and the low leg. And this graph here shows that the high leg had an average web temperature uplift of about 6.3 degrees, but the low leg was about 4.6 degrees. And we suspect that might be due to the greater wheel-rail contact area that you get from the high leg with the flanging that might be going on that. And the other thing that we confirmed, that empty trains barely show a blip on the radar. You get a very small change, if anything, 0.1, 0.2 of a degree, if you get something at all. They're pretty much imperceptible in the data. So how did we use this information? We wanted to work out what was our Armageddon scenario. What was the worst possible case, the hottest day of the year, totally sunny, no clouds, lots of trains running at minimum headways during the worst part of the day, the hottest part of the day. So that was our goal. So we knew how much a train contributed to rail temperature, or how much heat energy it put in the rail. And we used Newton's law of cooling as a model to indicate the temperature decay, because obviously where there's a greater temperature difference between the rail and the outside environment, that rail will cool down faster, and that rail cooling rate will slow as it gets closer to what the stable rail temperature would have been. And we're pretty happy with how this calibrated, because once it's got a K value here as a constant, and once we got that right and tinkered with it, we were able to get quite a good correlation, as you can see visually there, between the real temperatures we're getting off our sensors in the red and the model, which has been depicted in orange. So based on, once we got our model right, we're able to then go and say, all right, what if we had the hottest day of the year, cloudless day, trains running continuously at 20-minute headways, and we can get this line here, this little sawtooth line there. This is mapped on top of a winter day, or a spring day, sorry, I think, from this data. But we changed the baseline to a summer day, and we came up with this. So for all different headways, what is the worst case rail temperature we'd be expecting? And you can see why we haven't had a problem until the headways have gotten up, is because we're only now starting to break that back by getting the trains running closer together and in greater groups than they were before. And certainly we're seeing that groups of trains of about 7 in a row at 20-minute headways tends to get us very close to that maximum value. So from this, we have a design value. We know that 74 degrees is the highest likely temperature we have to allow our track to resist. And that's across the section. So we went to the next stage. Knowing that the predicted worst case temperature is 74 degrees, we tried to match that against what we think is our safe operating temperature. So we've got our design stress-free temperature here of 38 degrees. We know that that can go plus or minus 10 with the maintenance tolerances that we have in our track standards. From our CWR safe analysis, we were able to generate a number for 300-metre radius curves with the ballast profile that we've got, and that tells us that we've got about 47 degrees worth of track capacity. So that means that a well-consolidated track can increase in rail temperature by 47 degrees above its stress-free temperature. I hope I haven't lost anyone there. And before bad things happen. And there's other things there, so once it's unconsolidated, it loses it a bit. But we assume that the track's consolidated. We applied a 5-degree buckling margin of safety, and that brought us to 71. So the capacity of our track, nominal capacity is 71, but the worst case scenario is 74. We had a bridge to cross there. What could we do? And keep remembering that this is a model. We're really, in the real world, we're not going to be dealing with decimals of things, so there's a lot of engineering tolerances that have to be respected here too. So what we did, the last summer that we had was approaching, and what we did was we introduced some short-term risk mitigations. And the big one was 25-minute headways. Bring 25-minute headways in the summertime, but only between 11 AM and 4 PM, and only for loaded revenue services. So we went up the network operator and said that for 5 hours a day, for a few months a year, we need you to not quite run as many trains. They jumped up and down. They were quite unhappy about that. But we're happy to report that no trains were cancelled this summer. No buckles occurred this summer. It's a very good result. Quite happy with that. But obviously in a growing system where there's ever-increasing tonnage growth, that's not a sustainable solution, and we need to do something about it to improve for the future. So there's lots of options out there. There's lots of ways you can fix this problem, and it's a very interesting problem because there are so many creative solutions out there, but they all tend to revolve around these two key things of either reducing the temperature the rail gets to or increasing the strength of the track and its ability to resist that peak temperature. So we looked at things like increasing our design stress-free temperature, which we did do. We increased it by 4 degrees at Connor's range. But then you look at the capital options, and there's all these options such as reducing sleeper spacing down to 500 millimeters or 450 millimeters, which would do the job, but it would be extraordinarily expensive to complete. You've got things like bringing in these wing sleepers that the South Africans use, which have much greater lateral track strength, but again, very expensive. Sleeper replacement is not a cheap exercise. We can retrofit our existing sleepers with these modifications. And then we looked at some out there options. What if we brought in the water trucks? What if we set up an irrigation system and started cooling the rail? What if we brought in a bath, like a steeplechase for the trains, where jets come up and cool the wheels? Lots of different ideas, various levels of cost, operational cost, capital cost, whether it works, what benefit that will provide. But the answer that we did land on is something that we're working on now. We haven't yet set it up, but we're hoping to achieve something by this summer, where fortuitously, our track resurfacing machines resurface Black Mountain on average about twice a year. So what if we lined up those track resurfacing events so that they occurred in spring and autumn? So that in spring, we bring it from a wintertime alignment to a summertime alignment. Pull out those curves, say 30 millimeters, which increases the track stress-free temperature by about 10 degrees. And that makes the track more resilient to buckling in the summer. And likewise, when you go through in autumn, you bring that back to its wintertime alignment to protect it against uncontrolled curve pull-in and rail breaks that we're seeing in a lot of places as you get in those cold, crisp winter mornings. So that's where our headspace is at, and that's something that we think we can do at a very low cost, because it's an activity that we're completing already, and we have lots of monuments out there in the overhead electrification masts that we can get these offsets from. So that's where the story ends, and I hope you enjoyed it. If you have any questions, I'll be happy to answer some.
Did you look at any polymers that you could coat the rail with, the lubricator, to try and create a barrier between the steel?
We did. We did look at painting, actually. Some of the district guys ran out and did some painting. We found, yes, that did resist the solar energy, but it also acted as an insulator. So while it prevented it from getting hot from the sun, it didn't prevent the heat transfer from the train, and it retained that heat that it did get from the train longer by a small amount. So we decided not to continue that.
Daniel, your movement of 30 millimetres, was that sort of governed by your overhead geometry as well? Was it a limit that you could go to?
30 millimetres is the number we came up with. Mark Boyce is actually working away quite solidly on this project at the moment, trying to work out what is achievable with the known staggers in our network. Because it is a straight, it's not a cant change, it's a straight shift in track, it doesn't have too much of an effect on the overhead stagger as compared to if it was a cant change. Yeah.
I was going to say, that 95 degrees Celsius you mentioned at the start,
Yeah.
didn't come back through in your model or anything like that?
Because that was measured at the head. So that was
right
at the wheel rail
Not
contact
underneath the head,
surface.
yep.
So the wheel's 140 or 50 degrees,
Yep.
and it's heating the rail up to almost that, and there are about 400, 500 wheels in a train that
And
pass
your
over
others are
that.
measured under the head.
Yeah. So when the head's 95 degrees, the foot underneath the foot might be 30 degrees, and there's obviously a gradient of temperature through that rail. Does that make sense? Yeah. Sorry, Jeff had a question?
Yeah, Daniel, did you look at any infrastructure type changes like sliding switches like they use in Austria and places like that, where they have radical changes in weather between, obviously freezing and very hot temperatures at times, where they have the sliding switches to allow for the change in rail expansion?
The answer is no, and that's because we don't think they work. We have a... Sorry? Well, we have a network that uses 20mm E-clips, which have a very high tow load. So there's quite significant longitudinal restraint. There's obviously creep that occurs, particularly with the amount of trains we run. But we felt that the sliding rail would only provide a very localized solution at that point and would not change the stress situation further away from that point.
You've got to change your clips on either side.
Mm.
The tamping to move it across and back, is that not going to continue to lift the ballast profile? So this isn't a long-term solution. This will get you out of the hole for a couple of years. What's the long-term solution?
The ballast profile.
With that amount,
How do I
of
word this?
expect a bit of
Yeah.
consolidation as well.
We do lose quite a lot of ballast, and we do replace ballast at Black Mountain a lot, and that was the reason why we didn't think that would be too much of a problem.
Yeah, so you get to undercut it pretty soon.
Yeah, the undercutter does come through there quite quickly. What was the second part of your question?
No, that was it.
That was
Maybe a
it.
5 to 10 mil lift and you slewed across anywhere.
Yeah.
With all those spikes in temperature, you should actually, with your transmission metal downhill, you should have changes in stress temperature. Did you have the chance to install strain gauges on the rail and see how it was altering through time?
No, that is something we'd like to do.
Yeah, because you talk about temperature all the time. It would be good to see the variation in strain and see how it's actually modifying that.
We do have a creep monitoring program down the hill. There's actually a little hint of this in one of the slides where these brackets were installed on the overhead mast. Maybe I can't find the picture on demand. But there are little brackets on the overhead mast that shoot a laser down onto the rail, so you know how much that rail has slid. And that's measured every 500
You have
meters.
an experience of using salient modules, like strain gauge modules in Rockhampton. So, yeah, you could compare the results there and the results in this area to see like.
We're not seeing rail lose go anywhere near our lower tolerance over the time. So the other thing to consider in this case is that we replace rail every 3 years at Black Mountain, just simply because the amount of wear that we have on that track. So for that reason, we haven't had too many problems in that. It's quite fortuitous that the rail's being replaced and we're re-stressing it so much.
Sorry, I enjoyed your presentation. Coming down the hill, you mentioned 9 kilometres. Was there a certain number of kilometres that you found that your wheels were heating up and that transference really started to kick in? So is there a set of that gradient that is okay, and then, you know, as you said, it's down the bottom? Was it so many kilometres down?
So we noticed that the cluster of buckles were happening towards the bottom of the hill, because that's when the wheel had been through more and more rotations under braking. So more time to heat up the wheels. So there was that. We're also noticing that they were occurring on the, and it was a left-hand curve going down the hill, so that it was only the ballast shoulder there of that track, and it didn't have the ballast shoulder and the adjacent track to prevent lateral movement there. So we did see that sort of clustering. Does that answer your question?
Yeah, well, I'm wondering if it's heating up over that period and you had your sensors as you came down the hill. Was it after 7 kilometres that the wheel suddenly got hot enough that it was transferring through to the rail to have an effect, or was it 5 kilometres, or, you know, I'm just wondering how far down before you hit that?
We didn't do too many measurements towards the top end of the hill, but I did take one about midway, and I saw it was roughly linear in terms of the proportion of heating. Certainly the compounding would be much less at the top of the hill, because the rail does have the ability to cool down from that more mild level of heating.
Following on from that question, do you know that the wheels are cold at the top of the mountain, or is there some residual heat from the train running in?
We know that from every other hot wheel detector on our network, that wheels typically run around the network within 10 degrees of the rail temperature, except at Black Mountain, and except to a lesser extent at Tunnel.
Last few questions. You finished on time, Daniel, so unfortunately Peter's not here yet. So if there's any more questions, we need to spread it out a bit further.
Yeah.
I wanted to ask you about net creep down the range. Then you said you re-rail most of your curves every 3 years. So I was curious, with such a range, with such arduous conditions and heavy braking, are you seeing any evidence of an accumulation of rail creep down there, or is the re-railing actually negate that?
Can I defer this to Lachlan? Do you know much about
Not
that?
a great deal. There's not a great deal of creep, or you don't know?
Not a great deal.
No, the second option.
You haven't seen too much creep on the whole
Not
as a
really.
global.
No, but
Because obviously when we put new rail in,
replacing it every 3 years as well.
so when we put new rail in, we put that section to exactly the stress-free temperature. So that's reset at our design, and it can only fall or go up from there depending on.
There's no track creep goes to rail. You're not getting sleepers moving in.
Oh, that is a problem. That is a problem in these tight curves, and each mast has defined offsets, and that's actually where the winter and summer has come from. That we need to get better control over what those offsets are to maintain the alignment of the track horizontally. Yeah, that makes sense.
Yeah, Daniel, over at Rio Tinto, where the automated trains at the moment, because they've got unit trains and obviously robots trying to keep trains and with a particular speed area, they're actually going through and gradually over time bringing all their super elevation on their curves into true equilibrium as per the train is driven as opposed to the theoretical. Have you thought about doing anything seriously with regards to your super elevation and the range as well? Because obviously there's a lot of heat on the low level.
We've done quite a lot of investigations as a Aurizon network into super elevation on curves and where it's bad, where it's not bad, and where we should be doing something about it. With the exception of Hatfield, with the exception of the very top here, where they undertake brake testing, the truth of the matter is the range is actually pretty close to ideal. So I think most curves are canted at 45, but the equilibrium speed for most trains would be about 35 to 40. So you're not going to see too much benefit by doing that, especially compared to other places in the network that are so far more out of whack.
A horrible passenger trains, right?
North Coast line's a shocker.
All right, last question.
2 questions.
When
First one,
pizza arrived.
what sort of sleeper spacings do you guys run at? And the second one is, do you see a correlation? Because obviously you mentioned that 36 hours after you re-railed, you saw the buckle occur. Obviously your heart sank. I imagine the track wasn't profiled, the rail wasn't profiled or ground. When you grind rail, you obviously try to reach the optimum wheel rail contact. Wouldn't that mean that you would have a greater surface area of the wheel contacting the rail, hence increasing your temperature?
No, that's absolutely true. 685 is our sleeper spacing, to answer your first question, so it's quite generous by most standards. Yeah, it's close to the limit of what you'd really want to tolerate. But to answer your second question, yes, when we install the rail, it is installed to the factory AS60 profile. So rails are not ground until the next month or so, depending on when the next grinding cycle occurs. So yeah, it's probably quite certain that those rails weren't ground to the designed curve profiles at that time.
The as roll profile is quite peaky compared to what you grind your rails to. It would actually narrow the contact.
That's what I was getting at, yeah.
Would that make it worse?
I don't know.
I think
It's something we haven't really considered, to be honest.
And you talk that the contribution of the friction between the rail and the wheel was fairly light, significant. I think you said.
I wouldn't say it's insignificant, but it was it wasn't a majority player.
Yeah. I think it's the rail here.
I guess what we're getting at is the surface area between the wheel and the rail would be increased when your profile was established to what you wanted it to be.
And that's a good idea. That's maybe something we could be testing is with that chart that we had of the difference between high and low leg, what if we put that on a place that was recently re-railed and see if that scenario changes, if it means that it heats less because the contact patch is smaller, the contact band is smaller. Something we haven't looked at.
There are other things you want to consider in that, the effects on the rail.
They're re-railing every 3 years anyway.
Right. Can I just suggest that Daniel's going to stick around for a bit, so we can have a discussion after at the bar. Please stick around, drink, the bar's still open, and we've got pizza on its way. But I'd like you all to put your hands together for Daniel, because it's very interesting. And you know, it's showing great advancements in trying to find out why things are occurring on our network. Yeah, brilliant.
Thank you very much. Thank you.
A little gift from the people we like.
Oh, thank you.
No worries. Just a few housekeeping. You should have had an email about your membership. Unfortunately, if it's sort of sounding like you were all late, it was actually the first notification, but it seems to have prompted everyone to get onto it quicker this year. But anyway, if you haven't received an email, please contact me, and otherwise I'll contact you. So anyway, thank you, David.
Thank you.
Good,